Okay, so today we're going to be looking at linear and angular velocities. So if you're in class, you saw a little video introduction to this, the carousel video. And from there, we learned that there are two types of velocities. There is a linear velocity and there is an angular velocity. So what are these two things? Let's look at linear velocity. Linear velocity, or speed, is a distance that you travel in a specified time. You learned this back in grade school, usually with the formula, the distance equals the rate times the time, the rate being the linear speed or velocity, okay? So your rate would be the distance divided by time. You learned that in grade school, okay? What is an angular speed or angular velocity? Angular velocity is how fast something is spinning. So it is a swept angle in a specified time, okay? So the thing about this is that the angle is in radians. So let's tie all this together to what we did in the previous section. So let's look at our circle that we had before. And we have a radius of the circle. And we have another radius of the circle. And this shows an angle that is swept, a central angle of theta. Okay? And then this out here is a length on the circle, part of the circumference. So that is a length. We'll call that the arc length, or a distance. And so what is linear velocity? Well, based off of this thing that we did over here, using our terms that we have, so linear velocity, they usually use the letter V for velocity, and it is a distance. In this case, the distance would be S, and we're going to divide that by a time unit. And so what is angular velocity or angular speed? Well, it is how much of the angle was created in a time frame. So they use this little, it's not really a V, it's not really a W, it's kind of fancy Greek letter, okay? But it looks like a W, so we'll call it a W. So the angular speed is the angle that is swept divided by a unit of time. Okay? And the thing that you have to keep in mind here, very, very important, that angle must be in radians. It cannot be in degrees, it must be in radians to use this notation. Okay? So we have all these things. We've talked about velocities, angular and linear. Let's make the big connections here. Let's bring it all the way together. So what is the connection here? How can I do this thing? Well, we know from the previous lesson that the arc length, S, is equal to the radius times the central angle. Okay? This right here is a distance. This is a distance. This is an angle in radians. And we had this formula that we learned from before. S equals R times theta. Okay? That is a distance. That is a distance. And this is an angle in radians. Okay? So how do I make these into velocities and speeds? Well, I have an equation. I can multiply both sides by the same thing, or I can divide both sides by the same thing. So we're going to divide both sides by t. Divide both sides by by t, which is time. Okay, so if I divide this side by t and this side by t, so this is a product here, I can put it just underneath this one. And what you notice is I now have not just the length, I have, or distance, this now becomes a linear velocity or linear speed. And this becomes the angular speed or velocity. Okay, well, using the other notation that they use, they also write it differently. They use the v and the w. If v is this and w is that, then this equation right here can also be thought of as the linear speed equals the radius times the angular speed, where the angular velocity, remember again, angle must be in radians. So you have this formula and this formula, which is exactly the same formula. These are exactly the same. Okay, but you want to be familiar with both of them because sometimes you'll use one or the other one. You'll see how that works in some of the problems we'll do in a minute. So here's some things to keep in mind about this that caused errors for people in the past. We have different distances, and it's important to remember that the distance units must agree. And what that means is this: I can't talk about a linear speed, saying going 50 miles per hour, and then have a radius in inches. Miles and inches are not the same distance units. They have to be the same to continue this process. The time units must agree. Again, I can't be doing miles per hour and yet spinning, 300 revolutions per second. This time element is in seconds. This over here is in hours. They have to agree before you can continue on or even use this formula. And the last one, again, very, very important. Theta, the angle, must be in radians. Make sure you have it in radians. If it gives it to you in a degree, you got to change it to radians. This formula is very powerful because it's actually how, okay, this formula is how all machines transfer power. How they work, okay? You're taking rotational speeds, transforming it into linear speeds, and vice versa, okay? This is how they all work. So here's some things to keep in mind. And if you have different, scenarios and stories or whatever the case is, this right here can represent two pulleys, two wheels, two whatevers, and they're connected by a belt or a chain. Okay, so I have one circle or one pulley and another one. They're connected by a chain or a belt, like in your car. Okay, so as one spins, the other one will spin based off the belt. And then we have gears looking like this. This is usually how gears are done. We have two gears touching each other. One spins and then spins the other one. In these two scenarios right here, because they touch in some fashion, this one by a belt, this one by just actually touching, these circles will have the same linear speed. So that means the V part is the same for both of the circles. Even though they are one smaller than the other one or bigger than the other one, the radius is different, but the speed, the linear speed is the same. Because think about it. If I'm standing here on this circle right here, then it's like a treadmill. If I'm standing here and I'm running on the belt, I can run on the belt. The belt's not going to change speed as I get closer to this thing. It's still the same linear speed, still running speed. Okay? Now, the other one would be this one. And this is what's going on with the spinning action we talked about for the carousel. I have a circle inside of a circle, and they're attached in the middle here. This one has a radius. This is circle A, it has a radius. Circle B has a radius. Okay? So you got the big circle and the little circle, and they are attached. When they are attached, these circles will have, the same angular speed. The whole merry-go-round spins at the same rate. Okay, the outside horses might have to travel farther, but the inside ones, okay, travel farther, but they're still spinning at the same rate. The inside does not spin faster than the outside. See, it just wouldn't work that way. So these have the same angular speed. These types of situations have the same linear speed, and this is how you can connect and transfer power between different things. So this is what we're going to be doing. We're going to be using these formulas right here to answer questions dealing with linear and angular speed. So I have some problems we're going to work on together, and I'll show you how to go about solving these. So here's the first one. A belt connects a pulley of radius 8 centimeters to a pulley of radius 6 centimeters. Each point on the belt is traveling at 24 centimeters per second. Find the angular velocity of each pulley. Okay, so this is what we want to be able to do. So let's go ahead and start doing that. So we have our picture. Okay, and so each circle has a linear, each circle has this relationship. Okay, each one. Because both circles are connected by the same belt, traveling at the same linear velocity, we know the V for each circle. So for circle, 8 centimeter circle, it's 24 centimeters per second equals the radius, which is 8 centimeters, times the angular speed, which is what we're looking for. And this is going to be for, call it circle A and circle B. And I'll put it on here just so we know that this one is referring to the angular speed for A. Well, very simple. It's got 24 equals AW, so divide both sides by 8 centimeters. And what you're going to get is you're going to get the angular speed for circle A is 24 centimeters per second divided by 8 centimeters. We have to deal with units also. So if you look at that, this can then, I want you to see it this way. See it as fractions. 24 centimeters in 1 second. And then this is going to be flipped over to times 1 over 8 centimeters. Look what happens to the centimeter units. As if they were a number, they're going to drop out. Because remember, angular speed does not have any distance measurements in it. It only has a time element. 24 divided by 8 is 3. So we have 3 radians per second. So 3 radians per second. Now, angular speed radians is really not a unit. We don't really write radians, but we're going to just to keep our mind right. And we don't make misunderstandings. So I have 3 radians per second. And that is the angular speed for circle A. And we can do the exact same process again for circle B. I'm not going to do all this again. So we have, for the second one, we have 24 centimeters per second. And this one is 6 centimeters. And that's the circle B. And if I divide by 6, we can see that I'm going to get a 4. So the angular speed for circle B is going to be 4 radians per second. And there's that one. So that is the first question right there. Let's go down and look at the next question. So in this one, we have a mixing blade on a food processor. Think of a blender, okay? It extends out 3 inches from its center. If the blade is turning at 600 revolutions per minute, what is the linear velocity of the tip of the blade in feet per minute? Okay, so try and draw a picture. I have, basically think of a blender looking straight down. You have those little blades. It's going to spin, make a circle. Okay, there's the center. The food blade extends 3 inches from the center, so that means if I draw this radius, they told you that's 3 inches. So there's a tip out here. We're going to spin it around. It's spinning at 600 revolutions per minute. Now that's not an angular speed because it's not in radians, but it is related to angular speed. So we're going to use this to help us find the angular speed. Okay? And we want to find the linear speed. Write your formula down. I'm looking for V. I know R. R is 3 inches. And W I don't have yet. But I do know that 1 revolution around a circle is equal to 2 pi radians. We learned that in a previous lesson. This is a conversion factor that you can use to convert this to angular speed. Your angular speed is going to be this revolutions per minute, and then 1 revolution, and I offset it so the revs will cancel, and 2 pi, like that. This is how you use that conversion thing. Multiply this together, and you'll get your angular speed to be 1200 pi radians per minute. Okay? So we're going to take that quantity and plug it into here. 1200 pi radians per minute. Now the radian, like I said, is not really a unit, so we disregard it, ignore it. So we're going to end up with a velocity that's going to be in inches per minute. Multiply this out, and you get 3600 pi inches per minute. So that is the linear speed, but it's in inches per minute, and they wanted to answer in feet per minute. So we have to do a conversion again. If you don't remember, we know that there's 12 inches in 1 foot. That's the conversion for that. And so we're going to multiply this answer by a conversion factor, which is this, a ratio. I want the inches to offset, so then 1's on top here, so the other one's going to go down here. This is how you know where to put the 12. And then 1 foot on top. The inches, like a number, will cancel out. Excuse me, cancel the wrong thing. The inches will cancel out, and I'm left with just feet per minute, which is the answer form I want. You can use a calculator, work this out, and 12 into 3600 is 300. Pi is still there, and this will be in feet per minute. This is the actual answer. If you want to give an approximation, you can. All approximations are round to 3 decimal places, but I want to see the actual answer first. So 300 times pi, and you can put that out to 3 decimal places, and you can see that you're going to have 942.478, and that will be in feet per minute. So that is the answer, the actual and the approximate for that problem. This is how we do some of these problems, okay? Let's look at another one. This one, a little bit of history on it. You should look these things up. They're probably pretty cool. So the very first Ferris wheels aren't what we're used to this nowadays. These things were big, giant things, and they went really, really, really slow. Okay, and the cars that you sat in doesn't just hold 3 to 5 people. They held like 20. These things were huge. Okay, big old cars that people sat in as they went up and around. So this is one of the first Ferris wheels that was built in Reisenrad, the Great Wheel, in Vienna in 1897. It was 197 feet across in the diameter, and it took 15 minutes to go around 1 time. So it went really, really slow. Okay, we want to find the linear velocity of a person in the car riding on this wheel, and we want to get the answer in miles per hour. Okay, so we have our picture. If I'm going to do linear and angular speeds, which is what they're asking me to find, I have this formula right here that I'm going to use. I'm looking for the linear speed, so I need to know the radius, and I need to know the angular speed. So let's go work on those. Let's start with the radius. The radius of the circle is, this is a diameter, so it is half the diameter, 197 divided by 2 feet. And just leave it like that, you're fine. So that's R, and R is in feet. So now let's talk about the other one. So the angular speed, we don't have that. We have it's 1 revolution in 15 minutes. So revolution is related to angular speed. It's 1 revolution in 15 minutes. But 1 revolution is 2 pi radians. So this gives me an angular speed of 2 pi radians in 15 minutes. That is the number I can use. That I can't. So I have to use this number and this one. When I get done, I'll be in feet per minute. And that's fine. We'll change units to miles per hour after. So my linear speed is going to be 197 divided by 2 feet times 2 pi radians in 15 minutes. And so we can work this out and get an answer. And you can use a calculator, leave it as a fraction, whatever you want to do. The 2's are going to drop out. It's 197 times pi over 15, and that will be in feet per minute. Try not to use decimal work for this because you're going to do more stuff and you're going to lose out on your accuracy. We try not to use any decimal answers or rounded off answers in our work. We only want to save the rounding off answers for decimals at the end. Only round off your answer, never work in between if you can avoid it. So this is a number, it's a fraction, we just go with it. We want to convert this answer right here into miles per hour. So there may be some of these that you don't know. This will be in feet. This is 15 minutes. So let's start with the time. So I know, for some conversions, I know that 1 hour is 60 minutes. So that's one of our conversions. And then this is one you may not know. 1 mile is 5,280 feet. And you're going to want to remember these. These are your common ones. You should know these. So make sure you know these conversions. Minutes here, so minutes go here. Because I want the minutes to cancel out and leave me with 1 hour on the bottom. Right? It's miles per hour. So based off of this, my units are going to be feet per hour. So let's change the feet to miles. There's the numbers I'm going to use. I want the feet to cancel with what's down here. So this is how I know that 5,280 feet go here and 1 mile goes on top. These units drop out and I'm left with miles on top, hour on the bottom, and that's the correct units. At this point, you may grab your calculator. I don't need you to do all this by hand. We can just do our calculator, get an approximate value here. As long as I see this action up here, I'm fine. Type it all in. Use your calculator's fraction key. Makes it a lot easier. And just type all the stuff across the top. So it'll be 197 times pi times 60. And on the bottom, it's going to be 15 times 5,280. Okay? If you want, mine will reduce. If I hit enter, it'll reduce that fraction down to 197 pi over 1320. And that will be in miles per hour. Now, to approximate that, and then round it to 3 decimal places. So 0.469 miles per hour. So there is your response. So that's how fast it was going, half a mile an hour to make that trip. Okay? I got one more example down here. The bicycle wheel. Oops, you can see it. The bicycle wheel with a radius of 13 inches turns at 0.75 revolutions per second find the distance in feet traveled by a point on the bicycle tire in 1 minute. Okay, so as always, I recommend drawing a picture and identifying the information you have. So I have a tire. There's the center. It has a radius of 13 inches. It is spinning at 0.75 revolutions per second. That's my spinning speed. There's a point on the edge of this thing, and I want to track how fast it is traveling in a linear sense in 1 minute. Okay? So this is representing an angular speed, so we need to convert this to radians per second. So my R is 13 inches. My W is 0.75 revolutions per second. And then I'm going to change that to 1 revolution, 2 pi radians. And then we multiply this out. 2 times 775 is 3. So this is now 3 pi radians per second. So I can find the linear speed, okay, of that point on the tire by using the formula V equals RW. So I'm going to get 13 inches for the radius. I got 3 pi radians per second. And so my linear speed is going to come out in the form of inches per second. So this is going to be 39 pi inches per second. Okay? So I want to know the distance traveled, okay, in feet. Find the distance traveled in feet in 1 minute. Okay? So I can just convert the units inches to feet and seconds to minutes, and I should have my answer. Okay? Because this right here means 0.75 revolutions per 1 second. Okay? This is 39 times pi inches per 1 second. So if I convert this to minutes, then it'll be that per minute. Okay? And then I can just figure that out in that fashion. So here we go. So 1 minute is 60 seconds. And we already know that 12 inches is 1 foot for our conversions. So let's change it over here. Let's get it into feet first. So 39 pi inches per second. There's 12 inches in 1 foot. Okay. And if I do that, 39 pi over 12 feet per second. So I'll do that distance every second. So I want to know how long it's going to be for 1 minute. 60 seconds is 1 minute. And so multiplying all that out will give us the answer that we're looking for. And again, use the fraction key, always helps. You got 39 times pi times 60. And we're going to divide that by 12. And you can see that you're going to be going 612.611 feet in 1 minute per minute. So what is this? This is my velocity, and my distance traveled is just the top part. Remember, velocity is the distance over time. This is a 1 minute time. The question was, how far do I travel in 1 minute? So I travel 612.611 feet in 1 minute. And that's how you can answer that question. Okay. We'll be doing more examples together in class. So as of now, that's the end of this one.